This is the last lecture on the concept of damped harmonic oscillator, and you will see the discussion on a very important quantity which is called logarithmic decrement in this lecture. Okay, so what is this logarithmic decrement, how it can be evaluated, and in terms of this what we other quantity, how the other quantities can be evaluated, all these things we will see in this lecture. As you know, in case of a damped harmonic oscillator, the amplitude of oscillation decreases with time exponentially, and the relation how it decreases with time, you have already studied in the previous lecture, that if you consider that this A of t is the amplitude of our oscillator at any time t, and A at t equal to 0 is its amplitude at 0 time, then A of t is equal to A of t at t equal to 0 times e to the power minus bt, where b is called damping coefficient. And for convenience, we have assumed that at t equal to 0 the amplitude is a naught. So at any moment t, the amplitude a is given by a naught e to the power minus bt. And it is obvious from this result that the amplitude a decreases with time t exponentially. And this decrease in amplitude with time I have shown in this figure, which we have discussed earlier in very detail. Okay. Actually, this decrease in amplitude of the oscillator during the damped harmonic oscillation, this is actually measured in terms of a quantity which is called logarithmic decrement. So how this logarithmic decrement is defined? I have written the definition of logarithmic decrement here, but this definition will be clear to you after calculation. So how you can define this logarithmic decrement? Actually, logarithmic decrement is defined as the natural logarithm of the ratio between the two successive amplitudes on the same side of the equilibrium position or mean position of a damped oscillator, separated by one full period. So what has been told in this definition, wait for some time, it will be clear to you. So I am not clarifying this definition just now, but after making some calculation, this definition will be crystal clear to you what has been told in this definition. For this, let us consider a particle or an oscillator oscillating in a viscous medium, and I have shown in this figure that this O is the equilibrium position of the particle or the oscillator, and our oscillator has started its motion from this equilibrium position at time t equal to 0. And if this capital T be the time period of the oscillation, then time taken by the oscillator in moving from the equilibrium position to an extreme position is just 1/4 of the time period. So the oscillator will take a time, this t by 4, in moving from O to P1, where P1 is an extreme position in the right side. So I have mentioned here, you can see that at this position P1 the oscillator is at a time t by 4, and let us consider that its amplitude is A1, its first amplitude is A1. So according to this relation, what will be that A1? So at the place of A, you will now write A1, and at the place of time t, we will write t by 4, where t is the time period of the oscillator. So you can write A1 is equal to A naught times e to the power minus t by 4. Okay. Now the particle or the oscillator returns back to the equilibrium position, as I have shown in this figure. It comes to the equilibrium position and then it moves to the other extreme position on the left side, and again comes back to the equilibrium position. And in this journey, when an oscillator moves from the equilibrium position to an extreme position in one side, again it moves to the extreme position in another side and comes back to the equilibrium position. In this complete journey, time taken by the oscillator is what? This is capital T, which is called time period. This is definition of time period. And again, when it will move to the first extreme position on the same side, that is right side, then again it will take T by 4 time. So starting, if you measure the time from the start of the oscillator, that is from O, then this particle will return back to the extreme position in same side, that in according to this figure in right side, at a time T plus T by 4. Is it clear to you or not? You can see time taken by the oscillator moving from O to P1, and again P1 to this P2, and P2 to again O, that will be T. And from O to this P1 dash, I have not written P1 because some amplitude will decrease. So now the extreme position will be shifted to this position P1 dash. But time taken from moving from O to P1 dash now will be T by 4. So the total time when the oscillator again backs to this same extreme position is T plus T by 4. And let us consider that in this condition its amplitude is A2. All these things I have mentioned here, I have written, so you can note down these things in your notebook. Okay. So according to the same formula, we can now find what will be this A2. So A2 will be equal to A naught e to the power minus Bt, but T is now T plus T by 4. Okay. So you can see when you have written expression for A1, then in the power of exponential at the place of time there is T by 4, and for the second amplitude that at the place of time this is T plus T by 4. So time has been increased by T. So in this by induction you can easily say what will be the successive amplitudes of the third, fourth, fifth and so on amplitudes on the basis of equation 2 and 3. You can easily say. So on the basis of these results we can say that A3 will be equal to A naught e to the power minus B 2T plus T by 4. You can see when we have calculated A2, here is T, it means 1T. When you have calculated A1, there is T is not present, it means that is 0T. So when you will write expression for A3, there will be 2T. Okay. And when you will write A4, there will be 3T. Okay. So in the similar manner, you can say that for nth amplitude, An, what will be the expression? That will be A naught e to the power minus B times n minus 1T plus T by 4. Okay. So these are the expressions for the different amplitudes in the same side of during the oscillation. Okay. Now let us find the ratio of the successive amplitudes. You can see when we will obtain the ratio of A1 and A2, what will be our result? You can see A1 is A naught e to the power minus Bt by 4. And what is A2? You can see it here. This is A naught e to the power minus Bt plus T by 4. Okay. And so you can see this a naught and a naught will cancel out, this e to the power minus p b t by 4 will also cancel out. The only factor in the denominator will remain, that is e to the power minus bt, and that will be equal to e to the power bt. In the similar manner, when you will divide this a2 by a3, again you will see that in the the ratio will be same, and that will be equal to e to the power bt. Okay, so the ratio of the two successive amplitudes is constant, and that is equal to e to the power bt. Okay, you can check. And so I have written it here. You can see that the ratio of a1 to a2, a2 to a3, a3 to a4 all are equal, and that's equal to e to the power bt. Okay. Now let us take the natural log of these ratios. So this, taking natural log, this result can be written like this. This is log a1 over a2 plus log a2 over a3, sorry, not plus but equal, and that will be equal to log a3 by a4, and so on. And you know, when you will take log of this e to the power bt, this will be log e to the power bt, and this can be written as bt log e, but log e is equal to 1, so this will be simply equal to bt. Okay, bt, and we have assumed that this bt is equal to lambda. We have assumed, actually this quantity lambda, which is equal to bt, and you can see this is nothing, this is simply the natural logarithm of the ratio of two successive amplitudes in the same side separated by a one time period. You can see when we talk about a1, see the time is t by 4. Okay, when you talk about a2, time is t plus t by 4. So what is the difference of these two times? This will be t plus t by 4 minus t by 4, and that will be equal to t. So these amplitudes a1 and a2 are separated by a time period t. Similarly, you can also see when we will talk about this a2 and a3, the difference of these two times will be again equal to t. This you can see 2t plus t by 4 and minus t by 4. So this t by 4 will cancel out, and 2t minus t will be equal to t. So a1, a2, a3 successively are separated by one time period. So this is the natural log of the two successive amplitudes in the same side of the equilibrium position separated by one time period. And as I have defined earlier in the beginning of this lecture, that the natural log of successive amplitudes of the oscillator separated by one time period in the same side is called logarithmic decrement. You can see what I have mentioned earlier, you can see it here. This is the definition, and now you can see from that result what I have told in this definition, that is clear to you. Okay, so according to the definition, this lambda is nothing, this is called logarithmic decrement. Okay, I hope you have understand the definition of logarithmic decrement. So this lambda equal to bt is called logarithmic decrement. Okay, now you can see this logarithmic decrement lambda depends on the value of the damping coefficient, and as the damping coefficient depends on nature of medium, so if the same oscillator will oscillate in different media, this logarithmic decrement will be different because of the different value of b. Now let us consider a free oscillator. When you say free oscillator, it means an oscillator oscillating in a non-resistive medium. The oscillator is not experiencing any dissipative force. Okay, and for in that condition this damping coefficient b is 0. And you can see from this equation 5 as the logarithmic decrement lambda is equal to b times t, and in case of free oscillation b is 0, so lambda will be 0. So there is no logarithmic decrement in case of free oscillation. This is obvious because in case of free oscillation actually the amplitude remains constant, it does not decrease. Okay, that's why this logarithmic decrement has been obtained 0 in case of free oscillation. And so you can say why it is 0. It means log a1 over a2 is 0, log a2 by a3 is 0, and if log a1 by a2 is 0, what does it mean? It means a1 by a2 is equal to 1 because log 1 is 0. And so you can say that a1 is equal to a2. So in this case, in case of free oscillation, a1, a2, a3 and so on, all are equal. Okay, and so we simply say that amplitude of oscillation of a free oscillator is fixed and it is equal to a. Okay, now this lambda is related to b in this manner. Lambda is equal to bt, and so you can say that b is equal to lambda over t. So it is obvious that if we have the value of lambda known, then damping coefficient can be calculated. So damping coefficient can be measured in terms of lambda, that is logarithmic decrement. Okay, now in terms of this logarithmic decrement, you can find the value of this a naught, that is amplitude at t equal to 0. We can obtain it. You can see we have just seen that a1 is equal to a naught times e to the power minus bt by 4. Okay, but you have seen that this bt is lambda, this is logarithmic decrement. So you can write a1 is equal to a naught e to the power minus lambda by 4. Okay, and so a naught will be equal to a1 divided by e to the power minus lambda by 4. And taking this exponential factor in numerator, this result can be written as a1 times e to the power lambda by 4. Okay, now let us expand this e to the power lambda by 4. As you know, e to the power x is what? This is 1 plus x square over 2 factorial plus x cube over 3 factorial plus so on. Here at the place of x there is lambda by 4, and so you can write a naught equal to a1 times 1 plus lambda by 4 plus 1 over 2 factorial times lambda square by 4 square plus 1 over 3 factorial times lambda cube by 4 cube and so on. But lambda is a very small quantity. Its value is very small. And as lambda is very small, so lambda square, lambda cube, lambda 4, these will be much smaller. And all those values can be neglected in comparison to this 1 plus lambda by 4. Okay, so since lambda is very small, so all the terms inside this expansion of e to the power lambda by 4 containing the higher power on lambda can be neglected. So neglecting all the terms containing higher powers on lambda, what will be your result? Our result will be a naught equal to a1 times 1 plus lambda by 4. So knowing the amplitude in first throw, a1 is called amplitude of first throw. So knowing the amplitude of this first throw, we can find the value of a naught in this by the use of this equation. So this is a very important equation for finding the value of a naught, but this can be calculated by knowing the amplitude in first throw. That is, knowing a1, you can obtain the value of a naught. Okay, now let us try to find the amplitude of the oscillator after nth oscillation, nth oscillation. And if A1 is the amplitude of the oscillator after first throw and An is its amplitude after nth throw, then what will be this A1 by An? A1 over An can be written like this. This can be written as a product of A1 by A2 times A2 by A3 times so on times An minus 1 by An. Because you can see this A2 and this A2 will cancel out. Okay, similarly here there will be An minus 1 and this will be cancel out. So finally you will get A1 by An. Okay, but you have seen that A1 by A2 is e to the power bt and A2 by A3 is also e to the power bt, and this An minus 1 over An will be also e to the power bt. So all these ratios are e to the power bt. And what is the number of terms? Actually this is n minus 1. So you can write this is e to the power bt, e to the power bt, so on up to n minus 1 times. So you have to multiply this e to the power bt n times. So we will put a power n on it, and sorry, not n times but n minus 1 times. And so A1 by An, that will be equal to e to the power n minus 1 into lambda. And so you can say what will be An? An will be A1 divided by e to the power n minus 1 lambda. And so you can write An equal to A1 e to the power minus n minus 1 into lambda. So again you can see, knowing the value of the amplitude after first throw of the oscillator, that is A1, we can easily find what will be its amplitude in nth throw. So this is these facts are all about the logarithmic decrement, and I hope you have definitely understand clearly all the steps, all the calculations, and in this way I have completed all the concepts regarding this damped harmonic oscillator. But we will see in some important numerical problems which will be very important for different competitive examinations along with the university examination in our forthcoming lecture. Okay, thank you very much.